Okay, so the next topic is relative motion. Okay, and the rationale for studying relative motion is that, well, there is no such thing as absolute motion, right? So even though we say the velocity of an object is 5 meters per second, blah, 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 we pretty much always mean that the velocity is, say, 5 meters per second relative to something, right? So implicitly, when we report V or A, um, we are often assuming that those V or A are relative to the surface of the earth. Right, so when you say a car is going at 65 miles an hour, that 65 miles an hour is relative to the surface of the earth, specifically the road on which it's traveling. Okay, e.g. car at 65 mph equals relative to road surface, right? So really, we can only speak of relative motion and there is no such thing as absolute motion. So in all the problems from now on, when we drop the reference frame, in other words, relative to what we are reporting the velocity or acceleration, we can assume that it's relative to the surface of the earth. Okay, so assume if not specified. But of course, in particular situations, we may specify it, and of course, then you just go with whatever we specify. Okay, so we can only speak of relative motion. So here are the key principles of relative motion. So if you have two objects, A and B, then we say if, and then we define velocity of A with respect to B like so, as velocity of A minus velocity of B. Okay, and when we write it like this, of course, where these are relative to a common reference, example, Earth surface. Okay, so this is, so VA with respect to B is basically velocity of A relative to B. Okay, so this is a vector equation. So note, this is a vector equation. And does not work for velocity magnitude. in 2 or 3D. Well, let me just say velocity magnitude in general. Okay, so you should always use this as a vector equation, not as a scalar equation. If you replace this with the velocity magnitudes, it's not a meaningful equation. So that's how we define relative velocity. We can sort of make this more specific and say if you have 3 objects, A, B, and C, and then given velocity of A with respect to C and velocity of B with respect to C, and remember to put these bars on top so that it's made clear that they are vectors, then relative velocity of VA with respect to B is basically VA with respect to C minus VB with respect to C. Okay, so this is an important equation. This is an important equation. Another important equation is if velocity of B with respect to A, what is that going to be? That is just going to be the negative of velocity A with respect to B. Oops. A with respect to B. Okay, so it could be VA or VB minus VA, or in when there's a third object, it's going to be VA with respect to C. Okay. Okay, so those are all the key equations for relative velocity. These equations constitute what are called Galilean theory of relativity. So I'll put a box around this as well. These equations are called Galilean relativity. This name, of course, comes from the scientist, Italian scientist Galileo. From I guess the early 1600s and the late 1500s. As opposed to, there's another relativity, as you may have heard about in popular culture. What is the other kind of relativity you've heard of? Of course, Einsteinian theory of relativity, Einstein's theory of relativity. Einstein basically showed that these equations need to be modified when these velocities are very fast, approaching the speed of light, to make sense of mechanics. This kind of simple equation, which is what this kind of simple equation, which is what we had been using for the previous 300 years, need to be modified slightly when things go at very fast speeds. But for our purposes, we will just use these equations because our objects are not going at close to the speed of light. Einstein's theory of relativity is sort of more important only at those speeds. Okay, so this is for velocity, and then of course we have analogous equations for accelerations. So acceleration, again, we have the key equation. Acceleration of A with respect to B is if you have just 2 objects, or when these are relative to the Earth's surface. This is relative to Earth's surface when we don't specify what it's with respect to. And then if you have 3 objects, then of course A with respect to B is just A with respect to C minus A acceleration of B with respect to C. And of course, acceleration of b with respect to a equals minus acceleration of a with respect to b. Okay, so just to be clear, I'm going to say, so this is read as acceleration of a with respect to, okay. So that's it for relative velocities and relative accelerations. Like we said, important when we drop, when we just say velocity of A, velocity of B, we are implicitly saying it's relative to some common reference, which is the Earth's surface. And then we might specify it's with respect to something else potentially, and then we have to use this formula. And then we may occasionally need to use this formula where you're given velocity of A with respect to B, and then the velocity of B with respect to A, or the acceleration of B with respect to A is the negative of velocity or acceleration of A with respect to B, okay? So we might read this, just to be clear, we might read this as acceleration of A with respect to B, or acceleration of A relative to B. Right, so that would also be a fine way to say it. Okay, so that's the theory, pretty straightforward, and we can do some examples. So example, given example 1, given VA equals 2I meters per second with respect to some, say, Earth surface. And let's say VB is given to be minus 3I. Actually, let's make it minus 3J in meters per second, all with respect to Earth. Then compute VA with respect to B, VB with respect to A. So these are the two questions. We just use the formula. VA with respect to B is VA minus VB, which is 2I minus 3J, which is 2I plus 3J. And of course, VB with respect to A is VB minus VA. It's also equal to minus VA with respect to B, which is just going to be minus 2I minus 3J. Okay. Any questions about this? So that's it. So another example. Let's do a simpler example to get some intuition. So given VA equals 2I, VB equals minus 3I, what is VA with respect to B? Actually, let me, okay. So basically this object is moving to the right with 2 meters per second. Let's say everything is in meters per second. And this object is moving to the left with 3 meters per second. That's the negative sign. So VA with respect to B is going to be 2I minus 3I, and that gives us 5I. right? So the velocity of an object moving to the right with 2 meters per second with respect to an object moving to the left at 3 meters per second is actually moving to the right at 5 meters per second, okay? It's this velocity minus this velocity, but because this velocity is already negative, you get a higher velocity, okay? And this is the velocity with which these two objects are separating, right? So this object is moving to the right, this object is moving to the left. The separation velocity, the velocity with which the distance between them increases, is 5 meters per second. So, okay. Let's do another example, another really simple example. Example 3. So given, let's say VA with respect to B is 3I plus 4J. VA with respect to C is 2I plus minus 3J. Okay, so we have three objects, A, B, and C. We are given A with respect to B, A with respect to C, and then we are asked compute say, let's say VB with respect to C, VC with respect to A, okay? So what are these things? Well, VC with respect to A, maybe we can do that first. That's just going to be the negative of VA with respect to C. So let's do that. Minus of 2I minus 3J. So that gives us 2I plus 3J meters per second, okay? That's it. What is VB with respect to C? Well, we can write the formula. So VB with respect to C is going to be basically VB with respect to some common object minus VC with respect to the same common object, right? So the only other object that we have is A. So we say VB with respect to A and VC with respect to A. So that's basically VB with respect to C. So what do we know? We know VA with respect to B. So this thing is basically minus VA with respect to B. And then we do know now VC with respect to A, which is this thing. So this is minus of VC with respect to A is basically, well, I guess we know what it is. And minus of VA with respect to B is basically minus of 3I plus 4J minus of minus 2I plus 3J. So minus 3I minus 4J plus 2I minus 3J, which is going to be minus I minus 7J. And that's going to be the other answer. Okay. So make sure in your homework and exams that you underline and say, this is the answer, this is the answer. If you have part A, part B, it might be worthwhile circling things and saying answer for part A, answer for part B. That will make it easier for us to look through your answers and provide appropriate credit. So that's about the velocities, relative velocities. Let's do a couple of problems involving accelerations. So example 4. Example 4, we basically have, let's say, it's kind of a made up problem, as all of these things are. Let's say we have a slope, and slope with angle theta. Let's say theta is 30 degrees, but it doesn't matter. And let's say we have a car, and the car has some acceleration a. Okay, so this is the problem statement. Car on a slope has acceleration a with magnitude 5 meters per second square. So the magnitude of the acceleration is given, but the total acceleration is not given. And then we say someone drops a ball within the car and this ball, okay, let me actually back up a little bit and say as acceleration a with magnitude 5 meters per second with respect to the earth, right? So when we don't say with respect to the earth, that's what we mean. And then someone drops a ball within the car, and this ball has acceleration g equals 9.81 meters per second square in the vertical direction, in the vertical downward direction, right? And this acceleration is not with respect to the car, it's with respect to the ground. With respect to the ground. Okay, so this is just given to you. And then you're asked, determine A of car relative to earth, A of ball relative to car. Okay, so these are the things that we're going to ask. These are vectors. Okay, and we say this is the j direction, this is the I direction. Okay, so how do we proceed? So let's write down what is given. Let me use a different color perhaps. So given, what's given? First of all, we're clearly told that the ball accelerates relative to the earth with basically g in the downward direction. So let's write that as a vector. Acceleration of ball relative to earth equals it's 9.81 and it's in the downward vertical direction. So what is the vector? Is it j? It's going to be minus j. Okay, so this basically says that it's downward because there's a negative sign in the downward j direction. Okay, the negative j direction is this acceleration. And then we know that acceleration of a car with respect to Earth is basically, everything is meters per second square. This thing is basically 5 meters per second square. This is known. Acceleration of car relative to Earth is, the vector itself is not known, but let's just give it some unknown. Sort of components, unknown components. It doesn't matter what you call these components. I've just called them AX and AY. You can say AX car, AY car if you want, but it doesn't matter. Make something convenient that doesn't confuse you or us, I guess. As long as that's the case, that's fine. You can call it P and Q if you want, whatever, right? Don't call it X and Y because that suggests position, but if you call it some other variable, that should be fine. Okay, so that's the acceleration of car with respect to Earth. So let's just label these things, 1, 2, 3. So of course, using 3 and 2, what we're saying with 2 is basically that the square root of this square and this square is basically 5 meters per second. Or AX square plus AY square equals 5 square equals 25. Okay, so that's something that we're saying. Okay, what else do we know about the acceleration of the car relative to the Earth? We are told that the acceleration, while the car is moving along the slope, right? So the car has no acceleration perpendicular to the slope. The acceleration is only along the slope. Okay, what does that mean? So what does that mean? Well, if this is the acceleration, 5 meters per second, this is basically AX, and this is basically AY. So this is the magnitude of the acceleration, and this is the X component, this is the Y component, okay? And this is theta. A car relative to Earth is along slope. So this fact basically implies that this is basically the total acceleration, and this is the X component, this is the Y component. So we can say AX equals 5 cosine theta, AY equals 5 sine theta, just using trigonometry. We can plug that in 3. Let's call this 4. Use 4 and 3. So we have well, I suppose we don't necessarily, yeah, so I guess we have okay, so we have that. Let's call that 5. So, well, what is 5 cosine theta? If cosine theta is 30 degrees. So I said if we don't say whether something is in degrees or radians, just assume that it's in radians. But if, of course, we say something is in degrees, then you should just use degrees. So 5 cosine 30 degrees happens to be 4.33. And 5 sine 30 degrees happens to be 2.5 j. Everything, of course, is in meters per second square. Okay, because that's a of car with respect to Earth. Now we have pretty much everything that we need to solve this problem. We've already solved this problem, first of all, a of car with respect to Earth. So that's answer for that part. And then we have a of ball relative to car is basically a of ball relative to Earth minus a of ball or car relative to Earth equals minus 9.81 j. That's the ball relative to Earth. And then this thing is 4.33 I plus 2.5 j. And that gives us minus 4.33 I. And we have minus 9.81 minus 2.5, which gives us minus 12.31. Okay, that's ball relative to car. That's another answer. So this is kind of interesting, perhaps. So if the car is accelerating up, like so, and someone drops a ball, with respect to the Earth's the acceleration of the ball is going to be 9.81 meters per second square downwards. But with respect to the car, the ball will have this acceleration. So it actually will have this acceleration. So this acceleration is actually, well, potentially higher than the acceleration relative to the Earth, right? So because the car is also accelerating, specifically upwards, the ball seems to accelerate downwards faster, but also has an acceleration to the back of the car. So the ball will appear to go down in a sort of slope relative to the car's bottom surface. Okay, so that's the end of that problem.